Hello students. So today we'll discuss one of the important part in first year organic chemistry which is called as GOC, General Organic Chemistry. So what are the things which will come in General Organic Chemistry? What is a substrate? What is a reagent? How a reaction will happen? The basics of reaction mechanisms, all of the things you will be learning through GOC. These are the main basic concepts for an organic chemistry to be learned. See, we'll see what are the topics which are going to be covered today. The topics: fundamental concepts in organic reaction mechanism, what is a substrate and a reagent, what are nucleophiles and electrophiles, electron movement in organic reaction. So how this electron movement happens and what kind of electron movements will happen also will be see. Okay. So first part we'll see fundamental concepts in organic reaction mechanism. So what are the fundamental concepts in organic reaction mechanism? If you see, just like a normal chemical reaction, there will be a reactant, you will be having a catalyst, you will be having some other reactant. These both will be reacting to give you products. In the same way, in the organic chemistry also, you will be having the same kind of mechanism, but you won't be calling them as reactants. You will be calling them as substrates. So substrates are the one which you will be, it's like analogous to reactant in a chemical reaction. Same way, you will be having an attacking reagent. This attacking reagent will form byproducts, or the whole reaction will continue to give you an intermediate product, then you will get a final product. So you need to understand this intermediate product and reagent substrate. These three are important to tell what kind of products are you going to be getting it, what kind of mechanism it will follow, because many of the 99% of the reaction doesn't happen in a single step. There will be some chemical reaction will happening, you will be getting an intermediate product. It can be a one-step process, two-step process, or a multi-step process also. So you will be getting an intermediate. This intermediate will decide what kind of products you will be getting. So how to decide what kind of intermediates are there? Those all things we'll be learning it today. So a sequential account of each step describing the details of electron movement, energetics during a bond cleavage and a bond formation, the rate of transformation into rate of transformation of reactants into products. So what are the things which you are going to learn in a reaction mechanism? So what kind of reactants are there, how the electron movement will be happening, what is the rate of that reaction, everything will be learning in reaction mechanism. So there is an important part which you will be seeing here is called as bond cleavage. So what is this bond cleavage? How this bond cleavage occurs? Are there any types in this bond cleavages? We'll be getting to know today. So if you consider covalent bond, why do you consider a covalent bond here? Organic compound. What is an organic compound? See, if I say carbon, I have graphite, diamond. So what are these? I have graphite and diamond. These are allotropes of carbon. Then what are hydrocarbons? It doesn't mean only carbon is present in this organic compound. It means there is carbon, hydrogen, oxygen, nitrogen, and any other elements also will be composing of hydrocarbons. Mostly we'll be discussing hydrocarbons with carbon and hydrogens. So what kind of bonds will be formed in hydrocarbons? If you see, if you take an example of methyl CH4, you need to understand what decides what kind of bond is being formed here. You need to understand that there is an electronegative difference which decides whether it is an ionic bond or a covalent bond. If you have a barrier, above that barrier you will be calling it as ionic bond, below that barrier you will be calling it as covalent bond. That barrier is generally the electronegative difference, you will be taking it as 1.7 electronegativity, where difference value you will be taking it as 1.7. So I have electronegative values of hydrogen as 2.1 and carbon as 2.5. These are for Pauling scale. So now when you consider this difference, it is only 0.4 electronegative difference. So now you need to understand the value is very less. So it will try to form only covalent bonds. So what is a covalent bond? Covalent bond is just sharing of electron between these two atoms. Okay, carbon will give one electron, hydrogen will give one electron. So now this covalent bond also can take cleavage. So what kind of cleavages will it undergo? One is heterolytic cleavage, one is homolytic cleavage. So there are two kinds of cleavages you will be seeing in a covalent bond. So how does this cleavage occur? Let us see. So that bond fission, which you call it as heterolytic fission, when will you call this as heterolytic? When bond breaks so that both electrons go to one atom, giving ions that generate carbocations, carboanions, typically in polar protic medium. So let us understand this medium later on. You need to understand, you get a carbocation, a carboanion. What happens in a homolytic fission? Bond breaks, so each atom takes one electron, giving radicals. This is favored by heat, light, peroxide, non-polar solvents giving free radicals. So let us understand a little bit more. So if I call it as a heterolytic cleavage, both the electrons, carbon is giving one electron, hydrogen is giving electron, these two electrons will be taken away by one atom. So then, suppose if carbon is giving away its electron, such a way hydrogen is taking both the electrons. Generally this doesn't happen, but I am saying like both the electrons are being taken away, you will be calling that as C plus because it is deficient of electron. Now you will be calling that as C plus. So what are these ions which you got? The one with positive charge are called cations. The one with negative charge is called anion. Suppose if carbon is taking away those two electrons, then you will be getting a C minus there, which is called as carbanion. We'll be discussing more about this in the later slides, but now you need to understand you'll be getting ions and then it generates carbocations or carboanions, typical in a polar protic solvent. So how does this happen? This fission such a way, complete distribution of the charges, complete separation of charges is happening in a polar protic medium. What is a polar protic medium? In which the medium itself will act as polarity will be there in the medium. They will be helping such a way the bond breaks heterolytically. It will form ions separately. But in case of a non-polar solvents, this heterolytic cleavage doesn't happen. The atoms, whatever the elements or atoms, whatever is being participated in the reaction, they'll take away those electrons separately again. You'll be getting C free radical and H free radical. So these you will be calling it as free radicals, which are highly reactive. Why do you call them as radicals? Because they are taking their electrons away. These are odd electron species which are highly reactive, and also they are especially seen in non-polar solvents, peroxides, light. These kind of mediums you see them, you are calling them as radicals. Now, so let us see about carbocation. So carbocation you will be also calling it as carbonium ion. This word is very important, especially from NEET point of view and JEE point of view. If you'll see, this was asked once or twice in an exam. So what is the name of the intermediate product which you get? So they won't be asking you whether it is a carbonium or not. They'll be asking you, suppose if it is chlorine, you'll be calling it as chloronium. So that is an example in which they have asked in an exam. So these also can be asked. So you need to understand that these fundamentals are also very important. So let us understand what is a carbocation. Cation means it is a positively charged species. So carbocation, carbon is carrying this positive charge. Along with, usually it is a tri-coordinate compound. So sp2 hybridized, planar with an MTP orbital, and order of stability. Before going into the order of stability, let us understand each function of this carbocation. So it is a positively charged species. Why? It is giving away both the electrons of carbon which is there to the element which is accepting it. Now it is usually a tri-coordinate. Let us take an example of methane. Methane is CH4. So now once the bond breaks completely, you are getting CH3 plus. So what is this CH3 plus? Carbon with three hydrogens and one bond is being broken. So you will get a positive charge here. So it is surrounded by three atoms. This you will be calling it as coordination number. So that is what called as tri-coordinate. And it is sp2 hybridized. how to tell about hybridization. So we have done a separate video on chemical bonding, which completely explains you all the basic things, hybridization, MOT, VBT, Vespa theory, everything is explained detailedly in those videos. Now let us have a small idea of hybridization and why does it occur. Generally, when an atom has unpaired electron only, it will try to participate in bonding. So atom is having an unpaired electron, it tries to bond with, it tries to form a bond. Now let us take an example of carbon electronic configuration. You will be having 1s2, 2s2, 2p2. 1s2, 2s2, 2p2. So this is your electronic configuration. This is how your carbon electronic configuration will be. Now, without anything, carbon has two unpaired electrons. Did you understand? So now, carbon can form a bond with hydrogen. Hydrogen also has one electron, one unpaired electron. So it will try to form only two orbitals. Let us understand carbon as the smallest Mughal emperor. So they encourage mainly polygamy system. So carbon is ready to marry two hydrogens directly without any intervention of anything. So now carbon also has a chance of marrying many carbons. Why? It has an empty p orbital here. See, it's a planar with an empty p orbital. So what does this planar empty p orbital does? So it can make, seeing that carbon can marry more hydrogens, it will get excited. It will get excited and send this electron to this empty p orbital. You will be getting a electronic configuration which is called as this one. So you will be having 1, 2, you have this. So it is 2s, 2p. So there are 4 unpaired electrons. So after exciting that carbon can marry 4 hydrogens, it will get excited and form 4 unpaired electrons. So these 4 unpaired electrons, they will bond up with hydrogens to form 4 different bonds. 1, 2, 3, 4. But let us understand, so what is the use here? Just it is getting excited and it is forming 4 bonds. Then what else do you need it? Do you see it clearly here? When you take sp3 hybridization, when you consider carbon and 4 hydrogens, see, 2s orbital of carbon is participating with 1s orbital of hydrogen. So I have 2s here. The bonding is between 2s and 1s. The bonding is between 2p and 1s. Bonding is between 2p and 1s. 2p and 1s. So you have all bonds are different. This is 2s and 1s, 2p and 1s, 2p. When you see it clearly, this bonding is different from this bonding. This bonding, this bonding. These 3 are separate from this bonding. So what will happen? Actually, in this type of bonding, you need to see this bond length, this bond angle, bond strength, everything will be different because bonding type of bonds it is involved is different. But in a real sense, it doesn't seem any different. All the bond angles, bond lengths, bond strength are same. So how does this happen? Because of hybridization. So what is this hybridization? We'll get to know. So hybridization is intermixing of all these energies and forming. Just you put in a blender, you put all these energies together, you intermix everything and distribute all of them together equally such a way you will get 4 degenerate orbitals. So this is, I have s orbital, p orbital, I'll intermix these 2 energies, I'll get overall a mixed orbitals, 4 intermixed orbitals, each of sp3, 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 sp3. Why sp3? This is s and 3p orbitals. Combinedly, I am getting 4 degenerate orbitals. But in case of carbocation, I am removing 1 electron. So I have only 2s and p. So 1 s orbital and 2 p orbitals are there because one bond is already broken. So it is telling you that you get 3 orbitals, 1s and 2p orbitals. So it is sp2 hybridized. So I am getting 3 sp2 hybridized orbitals. That is why there are 3 bonds here. Now you understand one thing here. You will have a empty p orbital along with this. So now understand carbocation is like a person who is very hungry. Okay. Now carbocation, it is deficient of electrons. You need to provide electrons for it. So how do you provide electrons to it? You send an atom which is electron rich. You give food to the person who is hungry. So you give electrons, which is send a compound which is electron rich to it to make it lesser electron deficient. So how does this happen? For a carbocation which is electron deficient, I will send compound which will donate electrons easily. This is how it will increase stability. Okay. For this you need to understand a little about these type of compounds and mechanisms. So this is called as electron donating, electron withdrawing. There are some group of atoms which will donate its electron easily, which will withdraw its electron easily. So these we'll learn in the later cases, but you need to understand this point such. How do you increase the stability of a carbocation? So if there are more donating groups on the carbocation, it will feel very happy. Its stomach will be full. Now if you are sending lesser and lesser electron donating atoms, it will be little like the stability decreases slowly. So that is what this means. A tertiary carbocation, secondary carbocation, primary carbocation. So let us see how does this be. Suppose in a tertiary carbocation, I have one carbon with 3 methyl groups, CH3, CH3, CH3. I have a positive carbocation. Now you need to understand this methyl group will have plus I and hyperconjugation effect. So what is this inductive effect? Inductive effect is also a process in which electron donating or withdrawing tendency is seen in a separate way. And hyperconjugation is a process in which bond breaking and bond sharing electrons will happen in a different way. So these two processes help methyl to donate electrons to this carbocation. Suppose if I have the other one which is only 2 CH3 groups are there. I have this carbocation, I have one hydrogen, I have only one methyl group and 2 hydrogens. I have no methyl group. Okay. Now let us see. CH3 is highly donating than compared to hydrogen. For this case you consider, let us understand this point in a later cases, but for now you understand CH3 is a very good donating group compared to your hydrogen. How and why it happens we will see in a sequence. But for now you need to understand CH3 is a very good donating group compared to this. So this carbocation is very hungry. All are carbocations only. So CH3 is donating, CH3 is donating, CH3 is donating. How many are donating? 3 CH3 are donating. So this will be more stable. Here only 2 methyl groups are donating. Here only 1 methyl group is donating. Here there is no methyl group. So which will have more stability? If I consider, this will have more stability than this, That is what given here. Tertiary carbocation, secondary carbocation, primary carbocation and methyl due to positive inductive effect and hyperconjugation. Okay. This is about carbocation. Now let us see a case where another type of reaction intermediate which is carbanion. So what is this carbanion? If a carbon is containing a negative charge, you will be calling this as carbanion. So how do you decide whether it is containing a negative charge or not? Both the electrons are taken by the carbon itself. So you will get a negative charge. It is a negatively charged species. Generally tricoordinate. So here also you are breaking one bond, but you are having one negative charge on it. This negative charge can also be shown as a lone pair of electron because this is not participating in any species. See, how do you get a negative charge? I'll tell. So I have C like this dot, right? This hydrogen bond is broken and both the electrons are there with this carbon only. So this negative charge can be also shown as this lone pair. The carbon with a lone pair or a negative charge and there are 2 hydrogens. Now this tetrahedral structure it's an excellent structure. So if you understand this tetrahedral structure, see you see carbon, hydrogen, hydrogen, one hydrogen is there like this, other hydrogen is there like this. So imagine a carbon with 2 hydrogens in the same plane. this plane. Suppose you imagine it on the board. One hydrogen is towards you, one hydrogen is away from you. If you'll cut this plane in such a way, this hydrogen will be like same mirror image of that hydrogen. Okay, that is the beauty of tetrahedral structure. Suppose if you take these two hydrogens in the same plane and you cut it like this hydrogen which is there on this plane and this side of the board, they'll be like mirror images. Actually, I have drawn it in the same direction, but one will be this side, one will be this side. This also will get divided such a way they both are like mirror images to each other. Okay, this is the beauty of tetrahedral structure. You will understand more about this in chemical bonding. For now, you need to understand this is a pyramidal structure. What is this pyramidal structure? This lone pair repulsion will be more than your bond pair, Vesper theory. So it will try to compress it like this. So you will be having like a pyramidal structure. So 3 hydrogens will be like a pyramid in structure. So you have it is nucleophilic and basic in nature. Basic in nature means it can donate its lone pair. Nucleophilic site, which is electron rich, you will be understanding in the later case. Stability trend is typically resonance stabilized will be more than tertiary. Tertiary is generally lesser than secondary. Secondary is less than primary. Primary is less than methyl, which is opposite of carbocation. One misconception I want to clear it out here. See, it is given as opposite to carbocations. So now understand, tertiary carbocation is more stable than secondary carbocation is more stable than primary carbocation, because there are more donating groups. Carbon, which is positively charged, is highly hungry, it wants electrons. So there are donating groups, it wants electrons, something is giving electrons, so it will accept easily and will be very happy. But now when you consider carbanions, you don't think of this way, that it will be exactly of opposite, because here it is mentioned as opposite, but don't consider this thing as exactly opposite, because there are some structures which are carbanions are also stable and carbocations are also more stable, even if it doesn't follow this order. That is based on this property called resonance. So if it is a resonance stabilized, the carbocation can be stable or carbanion also can be stable. It doesn't mean whether it is tertiary, secondary or primary. But then why it is given here tertiary is more stable, less stable than secondary is less stable than primary? Because carbanion is already stomach full. It already has electron rich. It is already electron rich. Now something is coming to give electrons more and more to it. It doesn't accept it, right? You're already stomach full. Will you accept any more food? No. The same way, carbon also already when it is full of electrons, why does it accept other electrons even though there are electron donating groups, right? So here when you see, I have CH3, CH3, CH3. I told you these are electron donating. Already this is electron rich. Already there are 8 electrons in this. So generally it is completely filled. So if you break the electrons, I have 1, 2, 3, 4, 5, 6, 7, 8. There it is already octet. Octet is completely filled. So it doesn't want electron. But in case of carbocation, it is deficient of electrons. It has only 6 electrons in its valence shell. So it wants electron, it doesn't want electrons. So now this carbanion, even if there are many electron donating group, it doesn't want to be happy. It can't be happy because this will decrease the stability of a carbocation. You are already which is having rich electron, you are donating it more. It doesn't want that to happen. And now if I decrease this methyl groups, then yes, compared to this will be more stable. Now if I consider only one CH3 with a C minus. So there are hydrogens also. I am just showing you one methyl group is there, 2 methyl groups are there. Remaining are hydrogens. And there is only one methyl group which is CH3 minus. These two are called primary carbanions. These are secondary carbanions. These are tertiary carbanions. So now this will be more stable than this. And there is donating group compared to this. There is a donating group here. That doesn't make it more stable, right? It will become less stable. So this all will be dominated by a factor which is called as resonance. Okay. So what is this resonance? We'll understand it. And now let us see one more reaction intermediate which is called as free radical. Where does this free radical forms? We have seen it when there is a homolytic fission. So homolytic fission. Neutral species. So you don't have any charge on this. The charge on this is like you'll represent it only with a dot. So a free radical is represented like this. With a odd unpaired electrons on carbon, how does it become odd? Let us see. You have CH, CH and CH. There are 2 electrons here, 2 electrons here, 2 electrons here. What is the, how many electrons are present in the outermost orbital of the carbon valence shell? 1, 2, 3, 4, 5, 6, 7. So that is why it is called odd number of electrons on the carbon, usually sp2 like structure. So when we are talking about hybridization, I take hybridization with a factor is denoted by Z, which tells you number of sigma bonds plus number of lone pair electrons. So this is decided by Z factor to tell you about geometry and shape also. Shape you won't be considering lone pair. These all details are explained in chemical bonding. But for now, when you consider Z, hybridization includes only number of sigma bonds it forms. So now I have how many? There are 3 sigma bonds plus half lone pair. So you have a half lone pair which is 3.5. Generally many of the people will be saying like hybridization, here it is between 3 and 4. So it can either exist as sp2 or sp3. But most of the cases whatever you see will be in sp2 hybridized. So that is why usually sp2 like you will be considering it. So planar or nearly planar. This free radical, planar structures, you have seen the previous case also. This is also planar. This is also planar. Trigonal planar. All the carbon hydrogens are present in the same. Here also, mostly the carbon, you will be considering everything will be in the same plane. So that is why you will call planar or nearly planar. Stability order, tertiary free. See, this carbocation you consider in the same way. This is also a neutral species with electron deficiency. So now electron deficient means it is also hunger of electrons. So if there is a donating group, more donating groups are present, then here also the stability will increase. Either this can donate or this can donate. This, there are many probabilities for it to be donated by an electron. So here CH3, CH3 dot, CH3, C dot or CH3 dot. So this is deficient of electron. There is one donating group. This will be less stable than compared to this. This will be less stable than. So more are the donating groups for a free radicals and carbocations, more will be the stability. So here stability order is tertiary, secondary, primary, methyl. And due to hyperconjugation and resonance. This is because of hyperconjugation and resonance. Let us see about this hyperconjugation and resonance towards. So now let us do this question. Which of the following carbocation is expected to be the most stable? This is NO2 group. You have NO2 group. This structure is called benzene. So this structure is called benzene. You have NO2 group. NO2 is generally electron withdrawing group. So what is this electron withdrawing group? It has a tendency to pull electrons towards it more. So from the benzene ring, whatever is there, it will try to pull electrons from the benzene ring continuously. So what does it happen? If some atom is pulling electrons towards it, what will happen? There will be a positive charge which is being formed on the other element, and this is getting electron rich, so it will get a negative charge. This is called as polarization. It is pulling electrons towards it, so this will become negatively charged, that will become positively charged because it is getting deficient of electrons. So now this electron withdrawing group is pulling electrons in such a way there is a positive charge formation on the other things. So whenever it is pulling electrons, this NO2, there is also one more important factor which is called as meta directing. Right. So NO2. So what is this meta directing? Let us understand few basic steps related to it. We'll again come back to this in detail in the next part. So this is benzene. If there is any group on this, okay, this position is called as ortho. This position is called as meta. This position is called as para. Now you understand electron withdrawing tendency. this benzene is getting stabilized by a process called resonance. So what is this resonance? Continuously we are picking on this. So when a group is there, it is trying to pull electrons from this, especially at ortho and para positions, this benzene ring will get affected. So now suppose if something is coming to attack it, where will it attack? This group, if it is NO2, it is electron withdrawing, so it will be meta directing. So the incoming electrophile or incoming compound will try to come at meta position. In which of the following you are getting at meta position? This is not meta, this is ortho, this is meta, this is para. This is not meta, this is not meta. Only the compound which is there is this one, meta directing. So the compound is coming here. So the carbocation which is there is becoming stable here. He is asking which of the following carbocation is expected to be stable. How does it become stable? When there are donating groups nearer to it. So it is getting donated and then it is making it stable. Okay. This was asked in previous NEET. And it is very easy question. Once you get concept of all GOC, you will understand how to do this question very easily. Okay. Next intermediate product is carbene. So carbene is a neutral divalent carbon which has 6 electrons. See, even carbocation also has 6 electrons, but this is neutral and a divalent carbon with 2 bonds. Only 2 bonds are present. We were talking about this, no? Like carbon is having only 2 bonds and it has a lone pair or it has 2 unpaired electrons. This is after excitation. Either it has 2 electrons in the same shell or it has 2 unpaired electrons. Now, how does it happen? It is a neutral divalent carbon with 2 bonds and excess electrons. So you will be representing with CH2. Okay. It is highly reactive. There are 2 states in this. One is called singlet, one is called triplet. Singlet and triplet. These are 2 names. This singlet and triplet are the one which decides many factors. How do this compound, what kind of products will be coming? These all will be understanding in the terms of carbenes. When a reaction comes on this, I will be explaining you more about this. This adds alkenes to give cyclopropanes. This is an example of. So I told you, what are the different kinds of intermediates which are formed? Carbenes are one of the form of. Where do you see this? When this adds to alkenes, they give cyclopropanes. Generally, if I have propene, I'll add this carbon, or I have ethene, I'll add this to make it cyclopropane structures. Nitrene. Nitrene is also one of the intermediate product where you'll see nitrogen analog of carbene. It is same as carbene. You'll have neutral 6 electron nitrogen species formed from azides. Azides is N3 minus, also very reactive and can insert into CH bonds or CC bonds. So these azides also react. They form nitrene as an intermediate product. They react directly with CH or CC bonds. So they'll react with CC bonds, carbon-carbon bonds or carbon-hydrogen bonds, and they'll get directly attached to it. They are also very reactive. This is benzene. So benzene is also highly reactive. Dihydrobenzene with a formal extra pi bond in the ring. So how does this happen? When you take a benzene ring, so suppose this is cyclohexane. I think everyone know what is an alkane. This is cycloalkane. So in this cycloalkane there are 6 carbons, right? You have 2 hydrogens for each. 2 hydrogens for each. I'll remove 1 hydrogen from every carbon. So I'll get a structure which is like this. All one bond is broken, one bond is broken, one bond is broken, one bond is broken, one bond is broken. So from this, if you'll break, you'll get a structure which is alkene and like this. This is called as cyclotrihexene. But IUPAC, according to the IUPAC naming, you are not calling this as cyclotriene, cyclohextriene. You'll be calling this as benzene. Now from this benzene, there are one more hydrogen which is attached here. See, the structure will be like this. You have hydrogen, 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 hydrogen. You have 6 carbons and 6 hydrogen. The structure is this, and the molecular formula is this one, C6H6. Suppose if I take these two hydrogens away, I am getting, this is called dehydrobenzene. This is called dehydrogenation. You are removing hydrogens, so you will get one more pi bond here. You will get an overall structure which is this one. So this is called dehydrobenzene. So you will get an extra pi bond. It arises in certain nucleophilic aromatic substitutions. You will see in a special cases where nucleophilic aromatic substitutions are there. Generally, what are the substitution reaction, addition reaction? These all are reaction mechanisms. There are different kinds of mechanisms. There are addition reactions, substitution reactions, and elimination reactions. These all comes into picture. And in one of them, you will be seeing this intermediate product as benzene. Such halobenzenes with a strong base. So where do you see this reaction? Example is halobenzenes with a strong base. You will be seeing this kind of intermediate product. So these are about intermediate product. Let us see about substrate and a reagent. It is just like a normal chemical reactions. You will be having a reactant, you will be having a catalyst, you will be getting products. In the same way, I have a substrate. A molecule whose carbon is involved in the new bond formation is called substrate. Generally, the carbon containing compounds are substrates, and the one which is attacking it is called as reagent. So here, this is my substrate. CH double bond CH2. This is alkene. This is unsaturated bonds. It has an unsaturated bonds. So it wants to become saturated. What is unsaturation? It is deficient of bonding. Like there are only 2 bonds available. Carbon can form maximum of 4 bonds. It has formed the bonds, but it is unsaturated. Unsaturated means it is having a pi bond in it. Okay. Example, dienes, trienes, or you can say a double bond or a triple bond are unsaturated. Saturation is like all the bonds will be sigma bonds. Now, this wants to change as this. How does this happen? This reagent which is Br2, one Br will attack here, one Br will attack here, such a way you will be getting CH2Br, CH2Br. This is my product. In the same way, suppose if I have benzene, I have a reagent which is CH3Cl. This will get broken into Br plus and Br minus. In the same way, this will get broken into CH3 plus and CH3 minus. So this CH3 plus will attack benzene, it will form this product, and I will get other product which is HCl. So there is Cl minus also left, right? H from the benzene it will come out and it will form HCl. This is how a substrate and a reagent will like get reacted with each other to form products, these kind of products. So what are nucleophiles? What are electrophiles? These are general reagents. A reagent that brings an electron pair to the reactive site is called as nucleophile, and nucleus seeking reaction is called nucleophilic. So what does this mean? Suppose I have an electron deficient site, means I have a positive site. Suppose I take carbocation. Now this nucleophile is the one which has more electrons. It's an electron rich species. So this brings electrons to this compound to make it more stable. That is how the reacted site is called nucleophile. You can also represent it with Nu lone pair also, or Nu minus. Then it is a nucleus seeking site. Nucleus is positively charged. So it is nucleus loving. So nucleophile is electron rich and it is nucleus loving. So it loves electron and the reaction is called nucleophilic reaction. Now a reagent that takes away an electron pair from the reactive site is called as electrophile, and it is represented by E plus like this. Suppose I have E plus, I have an electron rich site, okay, or a lone pair. These two are there, and electrophile can attack here or electrophile can attack here. So I will be calling this as electrophile, which is electron deficient and loves electrons. So this loves electron, this loves nucleus. So electron seeking, and the reaction is called electrophilic. So this is a basic idea about nucleophile and an electrophile. There are so many things. An example, I'll tell you an example. A nucleophile is the one which can donate its pair of electrons. It can be either a lone pair of electron or a negative charge. Okay. Now let us understand the basic difference, which is called as Lewis base, Lewis acid. Now the statement which I dictate now or which I explain now is very important for as a basic foundation for the chapter which is called as acids and bases. Okay. Now, Lewis acid is the one which accepts a lone pair of electron. Okay. Now, Lewis base is the one which donates a lone pair of electron. So, how to remember this? One which donates a lone pair is called Lewis base. One which accepts a lone pair of electron is called Lewis acid. So, La, lone pair acceptor, Lewis acid. What is the use of this? So, we understand it wants electron. It is already electron deficient. It wants electron. So, all positively charged species, can I call them as electrophiles? No. You can't call all the positively charged, most of the positively charged species, you can call them as electrophiles. Now, how to decide whether it is an electrophile or not? You have compound which is CH3 plus. And this is general example, CH3 plus. Next, you have a compound which is NH4 plus, H3O plus. Can you call this as nucleophiles, electrophiles? No, these are not nucleophiles. So, sir, you said like which are positively charged, you can call them as electrophiles, but these are not actually electrophiles. This doesn't want any electrons here. See, nitrogen can form maximum of 4 bonds. Covalency is balanced, right? Now, it has a positive charge, so it can, what will happen is, in aqueous medium, this NH4 plus will get distributed or get broken into NH3 plus and H plus. The same way H3 plus also, H3O plus also can break into H2O and H plus. So, these provides electrophiles to the medium only in aqueous medium. You can't consider it everywhere. So, if someone says NH4 plus, is it a electrophile? No. If it is a H3O plus, isn't it an electrophile? No. In aqueous medium, NH4 plus and H3O plus can be called as electrophiles, but actually not. They are giving electrophiles, they are providing electrophiles. Okay, that is the difference. In case of Lewis base, one which donates, one more thing, can I call all electron deficient species as electrophiles? Yes, all electron deficient species are electrophiles. Can I call all Lewis acid as electrophiles? Yes. All Lewis acids are electrophiles. Can I call all electrophiles as Lewis acid? No. Understand the main difference between them. Suppose, first point, all Lewis acid are electrophiles. All electrophiles are Lewis acid. This is true, this is not. Because electrophiles, if I consider, they are deficient of species. All Lewis acid are deficient of species. That is why they are accepting a lone pair of electrons. They are called as electrophiles. All electrophiles need not be Lewis acid. Lewis acid are the one which will accept a lone pair of electron. But electrophiles need not accept a lone pair. Example, free radicals. CH3 dot. This is an electrophile. It wants only one electron to be formed. If I take CH3 plus, here this can accept a 2 lone pair of electrons. So, all electrophiles are Lewis acid. No, that is a wrong statement. Now, you also have all Lewis bases are nucleophiles. The same way, all Lewis bases can be called as nucleophiles, but all nucleophiles are not called as this one. Okay. Now, let us see a basic thing about how the notation is shown. Show the formation of reactive intermediates when following covalent bonds undergoes heterolytic cleavage. So, I have CH3, yes, CH3. Okay. This is my first case. Second case, I have CH3, CN, My third case CH3Cu. Try this question. Okay, done. So now understand, using a curved arrow notation, show the formation of reactive intermediates when the following covalent bonds undergo heterolytic cleavage. What is heterolytic cleavage? Complete breaking of bonds such a way one will take away the electron, one will become deficient of electrons. So now, which is more electronegative, carbon or sulfur? See, electronegativity is the one important factor which will decide everything in the reaction mechanisms. Many 90% of the cases are based on electronegativity and electron donating tendency of metals. So some basics of electrochemistry which is there in second year, some basics of chemical bonding which is there in first year is very much needed for your general organic chemistry and to understand reaction mechanisms. So you need to understand few basic electronegative values which are there in the textbook already. You see a table which is present. So understand, fluorine is more electronegative than oxygen, nitrogen has same, then chlorine, nitrogen and this has same, bromine, iodine, carbon, sulfur, pH, sodium. These values if you take, this will be like 4, 3.5, 3, 2.8, 2.5, 2.1, 0.9. These are very important things, especially these electronegative values are the one which decides whether you will be calling it as acid or base. Okay. Now, carbon and sulfur are directly bonded, carbon and sulfur are directly bonded. You break any of them, this carbon and sulfur, this carbon and sulfur. This carbon has 2.5, carbon and sulfur are almost having same electronegativity. But what will happen here is, sulfur, so if carbon takes away all the electrons, carbon is little smaller, right? Sulfur can take away electron, this carbon if it donates electron, you will be getting a charge which is CH3 plus and you will be getting SCH3, you will be getting a minus charge here. Anywhere you break, you will get like this, CH3 plus and SCH3 minus. So this is how your heterolytic cleavage occurs. So you will draw it with an arrow like this. This is how your heterolytic cleavage occurs. So now this one, how does it happen? This bond is broken, you will get a heterolytic cleavage. You will get Cn minus and CH3 plus. So here if I take copper, is given as copper. So copper will give away electrons to this. Copper is metal, right? It can donate its electron easily. Then it will become Cu plus and CH3 minus. This is how the heterolytic cleavage occurs in all of these compounds. So this is how you get ions in a heterolytic cleavage. So nucleophiles and electrophiles. They are giving justification, characterize the following molecules, ions as nucleophiles or electrophiles. So H, this is 1, this is 2, this is 3, 4, 5, 6, 7, 8. So there are 8 compounds given to you. You need to identify which of the following is nucleophile and electrophile. So we will categorize this as nucleophiles and electrophiles. So what are the points we have seen? Nucleophiles are one with negatively charged species or a lone pair. What are electrophiles? Electrophiles are positively charged species or electron deficient species. You need to understand, in an electrophile there is a vacant p orbital present. So let us see which is having a positive charge, which is having a vacant orbital. First let us see nucleophiles. Nucleophiles are one with a negative charge, HS1, HS minus, negatively charged species. CH2O minus, this is also negatively charged species, electron rich. Has a lone pair, electron rich, this is also nucleophile. NH2 minus and with a lone pair you will have. So these are electron rich species which are called nucleophiles. Let us consider the remaining things. BF3, because see, if you consider BF3, boron configuration, what is the boron configuration? You have 1s2, 2s2, 2p, 1. So you have 2 electrons like this, you have 1 unpaired electron. So suppose, now if it forms one more bond, this electron will get excited, you will be having a structure which is like this. So you will get 1 unpaired electron here, here, here. So BF3 will form 3 bonds, still you have 1 vacant orbital. This is also an electron deficient species, thus this is 5. Cl plus, you are removing 1 electron from the chlorine, from the outermost shell, you have 1 vacant orbital. Again, so this is also electrophile. CH3CO plus, this is the electrophilic site here. So you have C plus, 1 bond which is there for with hydrogen, it got broken because carbon needs 4 bonds. So this is like this, CH3, C plus, double bond O. Carbon is already deficient of 1 bond, that is you are representing with a positive charge. This is the electrophilic site here. You have next 7. Next, here also NO2 plus is also an electrophile. So 1, 2, 3, 4 are nucleophiles, 5, 6, 7, 8 are electrophiles. Let us do this question as a homework. So we'll end our class here. We'll continue the next topics which are, we'll do few more questions which are directly NEET based questions, NEET PYQs. Then we'll go to the next topic which is electron movement. Okay. So do this as a homework. This is a homework question. Okay. That's all for today. Thank you. So we'll end our class here. Do this as a homework. We'll continue in the next class with the next topic. Thank you.